Okay, so I'll be frank, I'm really tired right now. But it's now or never, so we're just going to do this thing. Okay, so I'll be solving two problem sets from this PH507 course. In fact, those are the only two problem sets that we have been given till now. But let's just go through them, like sort of speed run, if that makes sense. Okay, so first problem set, and like the first question is about ideal gases. So first you have to so it's question one is like about ideal gas, and the A part is that show by explicit use of the equation of the adiabat that we derived in the class. So I guess I'll derive it as well, that the efficiency of Carnot engine with ideal gas is eta equal to 1 minus Tc upon Th. So now for a reversible adiabatic process, we can obviously use this equation Te equal to Tds. We can in fact always use this equation, but there's like some cool stuff about this. So minus PdV, right? So notice that this term just goes to 0 because it's an adiabatic process, so then we can just say that TdS is exactly equal to dq. So then this is just the remaining stuff, right? So minus PdV. So yeah, we just have d equal to this thing, but then you know that the energy for the ideal gas is given as a constant, so let's just say F by 2 times the pressure times volume thing, which is obviously proportional to temperature, but essentially it's just this thing, right? So PV equal to nRT for ideal gas, that is like kind of the basic thing, the equation of states. And we also know that the energy is given as a directly proportional to temperature, so that essentially means that energy is proportional to the pressure times volume. So we'll just say it's F by 2 PV, where you till now don't have to worry about what F is, but later on you'll see it's just the degrees of freedom for each particle, but whatever. So now that you have equal to F by 2 PV, what we want to do is just put that over there. So you just wait a second. Alright, so what was I doing? Right, so now just put dE over there, so essentially just get F by 2 PdV plus F by 2 VdP, that's equal to minus PdV, whatever. So you combine these terms and essentially just get like dV upon V, that times of this comes over there as F plus 2, and that's equal to F negative, in fact, right, or you could just say plus over there, so it doesn't really matter. So plus F so dP upon P, that's equal to 0. So then you just integrate this thing and essentially what you get, so just like divide this over there. So just call this whole factor as gamma. So you just get like integrate this thing, just get like natural log of P upon P naught plus natural log of V upon V naught times gamma. This thing is equal to 0. So essentially you're just saying that PV power gamma is sort of some sort of constant, and that's like, this is very basic. But now using this, we want to find the efficiency for Carnot engine, and once again this is like really just manual labor. We already know that the efficiency is going to be that for any reversible engine, but we'll just do this because practice makes perfect, I guess. So let's just go. So suppose you have been given some initial state P naught V naught. So this is just some arbitrary cycle, we don't really care. So what you do is first this, I guess it doesn't matter what order we do it in, does it? No, I don't think it matters. So wait, so you will be expanding, right? Okay, so let's just think of a piston, and let's just think that okay, it has just been squeezed all the way down, and then now it's gonna be at some higher temperature, and then it will just relax itself, and then we'll close this thing, this heat transfer thing, and then it's gonna relax it even more, right? So this whole thing is an isotherm, and this whole thing is an adiabat. So from here it goes to something, we don't really care. Oh, this whole thing is also an isotherm, by the way, right? So it goes to some right, so the volume will change and all that. Let's just say the volume is now V1, so V1 upon V naught, yeah, whatever. So V1 upon V naught, and over here you should just, sorry, the volume is V1, right? So V1, and this should be P naught times V naught upon V1, right? Is it correct? Yeah, I guess, because right, this is correct, in fact. Okay, so it just becomes that. Let's just call this thing as p1 v1. So then, okay, we already used that. So let's just call this thing as, oh, let's just call this as v0 dash or something. Whatever, let's call this v2. This is 2. Let's call this p1 v1. Then this whole thing is p1, and this is p2 v3. So this is v3. This will be just v1 upon v3. Okay, cool. Now we can use the fact that these two are area bets and just say that, okay, pv power this stuff. Right. So let's just start. So what you essentially have is that pv naught v2 power gamma minus 1, that's equal to p naught, sorry, equal to p1 v1 v3 power gamma minus 1. Cool. And you also have p naught v0 power gamma minus 1 equal to p1 v1 power gamma minus 1. Amazing. So from here what you can sort of do is just cancel out these p1 guys, so you'll get some sort of a relation between v0 v1 v2 so on. This should be v1, I suppose, right? I guess, yeah. We can't say anything more about this, can we? No, we don't. I don't think we can. Anyway, so what is the work done? Well, it's just this, just add the work from each of these, right? Yes. What's the heat transferred? Well, this was an adiabat, and this was also an adiabat, so there was no heat transfer during these guys. The only heat transfer was over here, but then that was at constant temperature. And oh wait, so we kind of need to know what is the heat transfer for an reversible isothermic process, right? So I guess first we'll need to derive that. This is going much more into, right, much more problematic, but anyway, let's just do this thing. So dq equal to de minus dw. In this case it's just plus pdv over there. Well, d is not there, so you essentially just have this equation, right? So the heat transfer is just the integration of pdv, which is now like just depends on the temperature, obviously. But since now, yeah, let's just say integration pdv, and it's going from p0 v0 to some other thing, p1 v1, like anything really, just, yeah. Right, so it obviously has to be that p0 v0 is equal to p1 v1. So you can write this p thing as sort of just changing with respect to this. So just p v upon v0, that terms of dv, right? Yes, I suppose that's correct. Am I messing up some? Right, I am, sorry. Obviously we want our pressure to not be varying, so just p0 v0 upon, the pressure term to not be varying. So this thing is just like p0 v0 natural log of v going from there to there. So just v1 upon v0, right? Yeah, essentially. So this thing is just like constant throughout the adiabat. Isotherm doesn't matter. Anyway, so that's the heat transferred. Okay, so q is just this thing for an isotherm. For an adiabat, what's the work done? So now once again your dq thing is 0, so just like de equal to, yeah, so right, that's just the thing, right? What's the work done in that case? So you can write it as it's just the same thing as a change in energy, essentially, right? And how much does the energy change? It just changes as p1 v1 minus p0 v0. Okay, that's weird. All right, this times of f by 2, but then we sort of know some relations between them. Right. So the whole plan is to just write essentially everything using p0 v0 and p1 v1. God, I wish there was a better way to do this. You know what? Whatever. This is okay. This is completely fine. I'm not going to go about this. So yeah, we can use these two equations to sort of get some information. So first you have this thing. It relates p1. So now you know what p1 is. P1 is just p0 times v0 upon v1 power gamma minus 1. Well, now f plus 2 upon f is what gamma is, right? So you can write that whole thing as 1 plus 2 by f. So this thing just becomes like 2 by f over there. I guess I'll just keep it like that for now. So just, yeah. So now you can just replace that everywhere. So instead of P1, you can just have this new thing, you know, P naught and then all of this stuff. So P naught V naught upon V1 power down minus 1. Amazing. Obviously, there's gonna be 1 minus gamma. Anyway, so over here as well. And I guess you can do the same thing for the other adiabat as well. So now once again, just P naught upon V1 power gamma minus 1, right? So this equation is like used up at this point. It doesn't matter. It's redundant now. And once again, you use this equation, I suppose. Yeah, right. So now you can kind of just plug in what P1 was. So it's just P naught V naught V2 power gamma minus 1 equal to. So there is no, in fact, P2 at this point, right? No, there isn't, because you have already used that. So this will sort of nullify the V2 thing over there, and just write everything using just that. Right. I'm just gonna write it over there. So this is P naught V naught upon V1 power gamma minus 1. Okay. V1 V3 power gamma minus 1. Amazing. So what does this give us though? Well, P naught cancels, so it just gives us this relation, which is okay. What do I do with this? It's relating V2 and V3 essentially, I guess. Yeah, well, so we want to write everything using just just 3 variables, right? P naught, P naught, V1. So we'll try to nullify this, and V2 as well. Let's just take V2 in there as well. So then we just want to find V3 essentially. So we'll just have V3 power gamma minus 1 is all of this stuff. Not a good idea, is it? Yeah, it doesn't matter. At any rate, this is going to be very bad. But let's just do this thing. So it's just V3 equal to what? So it's V3 equal to V2. Sorry. V2 times V1 upon V0. God. Oh, this is going to be harsh. And V0 upon V1 to the power of 1 upon gamma minus 1. Okay. That's not good. But fine. So you got V3. And now this equation is also redundant. So now you have all the information that you need. Also, you kind of need the work done. So, but that's okay. That's just the change in energy, right? Okay. So what we want is the total work done upon the total amount of heat exchanged. So this is the heat exchange, right? This is for an isothermal process. Well, this is an isothermal, and this is an isothermal. No, wait. This is an isothermal process, and then this is an isothermal process, right? So the heat that we take in fact, we don't even kind of want the heat that we give out. So in this thing, we are, I suppose, taking in heat, right? Your volume seems to be increasing, so I guess, yeah, you're just taking in heat, and so this is the thing that will come in the denominator. And also we kind of want the only process we're giving out work. We are not, no, wait, no, that's not right, is it? In the part where it is taking work, it is taking work. Yeah, right. So that we still have to include. So just put that over there. So just P naught V naught natural log of V1 upon V0. Now, yes, this is a whole confusing thing. Like, what is this to do? So in fact, we kind of want everything in terms of temperature, right? Yeah. Oh, we already messed up. But just think about it. What is T7 minus TH? It's just 1 minus, so the temperature of this isotherm, which is sort of proportional to P naught V naught upon pH. So this thing, which is proportional to this, well, this is the same temperature, so you have to use one of these guys. So just P naught V naught upon V1 power gamma minus 1, and then again a V1, right? This is what we want. So how does this natural log stuff come in? How are we going to get rid of that? Wow, that's a hard question, isn't it? Yeah, that's a problem. Okay. A natural log, unfortunately. This is not cool. So we want the heat input, right? And that's certainly just this thing. We can't even do anything with it, right? So we want to show that for convection the efficiency is just this. Well, then there should be some other, natural log thing which we didn't get apparently. How come? How come we didn't get anything like that? Then this is just equal to the work done. It's just PdV. Yes, it's just PdV. And yes, that does give us natural log. That's okay. What about the work done in an adiabatic process? Because the heat is gone. The work done in an adiabatic process. Wait, I think this could have been much simpler, because notice that you know that both of these isotherms are at different temperatures. Well, in each adiabatic process, what's the work done? It's just a change in energy, and you're going from one temperature to other temperature and then just going back. So like the work done in this and that just cancels. Oh, we really just didn't need to do that. Wow, that's amazing. Wow, indeed. Uh-huh. Anyway, and the work done in these processes is just the negative of the heat. So we didn't really have to do any of this, but in any case you just have minus p naught v naught natural log of v1 upon v0. So by the way, this thing that we're talking about, it's this process, right? Yeah, amazing. So that's like v thing is increasing, right? So it is taking in heat. Yes, and it's doing work. So it's negative, like the work done on this is negative, if that makes sense. And over here so I should be putting that as positive, I guess. And then here just have the negative of that thing. So once again, just anything from here. So just v1 upon v3 at this point. Yes, which we can write as negative, so because that was there. Alright, so it's like that. Now it's just plus p naught v naught upon v1 power gamma minus 1, and then you just have natural log of this v1 upon v3. Now it's going to be v3 upon v1. Amazing. So essentially we just need what v3 is for some reason. Oh, this is easy. It's just v2 upon v naught and then all of that. But what's v2? That's a whole other can of worms, isn't it? Sure is. Yeah, so to get v2 you would have to do something. That ain't good. That ain't good. Natural log of that, right? Amazing. So this is just v0 v1, nothing complicated really. And once you put that over there, right, like what v3 is, and you just want natural log of this whole thing. Now that's weird. So it's just v2 upon v0, and then you got v0 upon v1 power 1 upon gamma minus 1. How can we use v2 upon v0? Where are we using v2 upon v0? Wait a second, this whole thing is an isotherm, right? It should not be v1 over here, it should be v2. Sorry for that. Yeah, this should be v2. Makes sense. This is an adiabat, no heat. This is an isotherm. Yes. Cool. So now it makes sense, because this v3 upon v1 thing, this is just this, right? Which is just v2 upon v0 and all of that. So put that in the natural log, you just essentially get natural log of v2 upon v0, right? I also have this thing, right? Yeah, p0 v0 power gamma minus 1 and all that stuff. We kind of don't want that. Yeah, we want to eliminate the v1 from here. How would you do that in that case? Yeah, you probably would have to rely on that. That's not good. Oh god. So you can't eliminate the v1, unfortunately. Okay, first of all, just simplify this thing. So what does this become? It just becomes 1 plus. So the p naught thing cancels. So just got this stuff. v naught upon v1 power gamma minus 1 natural log of v3 upon v1 upon natural log of v2 upon v1. Okay. So v2 upon v naught, sorry, not v1, right? This is the result that we're getting. Now we just need to show that, well, one thing is that this term should just sort of like give us this gamma minus 1 factor, and this term should just sort of die basically. No, it's obviously not going to die, right? Yeah. So just why are we writing this, by the way? I kind of forgot. So it's p naught and then v naught upon v1 power gamma minus 1, right? That's just the pressure. Where's the volume part? Oh, obviously you need this v part. Yes, obviously. Come on, don't make these sort of mistakes. It should be v1 over there, and then just put what v3 is, and things will turn out the way they should. Now we just want v1 in terms of v0, right? Well, you can get that from there. Oh wait, you have a p1 over there. That's a problematic thing, so that's not cool. So you want v1 in terms of what, v0, right? And v2. Okay. Shouldn't be so hard. Alright, so if you return pressure means that. This whole v3 thing is like really just on my nerves, sort of. Yeah, right, so just v3 upon v1, that's the thing, which is what, v2 upon v0, and then this whole v0 upon v1 power gamma minus 1. That ain't nice. v0 upon v1 power gamma minus 1 is certainly not a nice thing. Can't you have v2 in terms of v1 somehow? Well, also you should probably have a v1 over there, so just, you know, just there. Yeah, right, so it should be v1 upon v0 in fact. So you have this minus 2 factor in this case, right? Oh wait, okay, no, that okay, interesting. Yeah, okay, you do have a minus 2 factor. Cool. Okay, I'm losing hope. What was this one? It's been v1 upon v0. Amazing. Yes, this was in fact v1 upon v0. Yeah, right. So what is remaining? Why is this? So you want natural log v3 upon v1. Okay. v3 upon v1. What can we use though? And you can use the fact that the energy changes are just same, right? In the adiabatic processes. Yeah, that. Okay, I mean, we kind of already used that, right? Okay, how is that even helpful? Yeah, the energy changes are the same. Now that doesn't look to be very helpful. The only real thing that we should be using is the fact that you have an isotherm adiabates and all that, right? So did we mess up somewhere? We're just using v2. This is using v1. So you don't want to be using of these guys. So you know what v3 is in terms of v2, v0 and v1, but what we need is like what v1 is, right? The p0 stuff like cancels in any case, so that's okay. So you're going to have 4 equations, and the number of variables that you have is 8, right? Yeah, so that's going to reduce to 4 variables in the end. Now for 4 variables, well, one of them dies in any case. So essentially what you want is to write everything using v0, v2 and v1. That should give you a constant. It's not giving me a constant. All of this is in fact just using v2, v0 and v1, right? Yes. So why is this not working? Okay, let's just actually put in v3 and see what happens. So v3 is just this thing, so you can just write it as v2 upon v0, v0 upon v1, the power of 1 upon gamma minus 1, right? Put that in there, so just like natural log of v3 upon v1. That's what v3 upon v1 is, by the way. This is gonna give us two factors, so it's just 1 plus v0 upon v1 power gamma minus 1. You should probably also have that. Yeah, so it will actually just give us gamma minus 2, most likely. I'm getting like some really bad feelings from this. Yeah. Okay, wait. What do we want again? We want 1 minus tc upon t. We'll get to it. I guess we'll get to it. Okay, so we're just 1 plus v0 power of gamma minus 2, all that stuff. And then this whole thing, what does this turn out to be? So you put a natural log, so this is just 1 plus 1 upon gamma minus 1, natural log of v0 upon v1, natural log of v2 upon v0. Amazing. That's just how it should be. Cool. Now what? v1 upon, okay, this is not cool. I suppose this is in fact a final form. Let's just think about it for a second. So all these natural log terms, right? Those are the ones which are really just messed up. The v2 upon v0 thing just cancelled. Yeah, that's not a problem. Damn, if this was just that. Yeah, if this was just that would be so much better. If you could just write as v3 upon v1 equal to v2 upon v0, that would be better, right? Well, why is this equation coming in the first place? I suppose it's coming from one of these p0 things. One of the isotherms indeed. So you have this and you have that, right? These are adiabats and then these are isotherms. So you just have right. Okay, this is obviously an isotherm, so that equation is just valid in any case. And you just have p times v is equal to p times v over here in this isotherm. And what does that give us? Well, that just gives us, heck, this isn't what it gives us. Right, okay, it makes sense. No wait, we kind of used up that equation because this is trivially true. That didn't help. What was the equation that we kind of used? Okay, so this is an adiabat and that we have already used, so no problem with that. Okay, this is so this is the last equation, right? So it should have been like, okay, let me just write down that equation again. So this would be something like, let's just actually shrink this whole thing. Okay, so you would have something like, oh come on, why won't it? Okay, so this is not working. I'm just gonna copy this whole thing. Okay, cool. So our equation would be something like p0 v0 upon v2 power gamma, right? That's equal to this, then v3 power gamma. So p0 v0 upon v1 power gamma minus 1, v1 upon v3 power gamma minus 1, right? It's quite a bit of stuff involved. So it's just v2 power gamma minus 1 over there. This is just, right, okay, now it will be v3 power gamma minus 1. Cool. Let's have this v1 term, p0 cancels. So what do you have? Wait, there's also v0 over there. So just have v0 v2 power gamma minus 1 equal to v naught gamma minus 1 v1. That's in v1 over there, isn't it? Wait, is that right? So v1 upon v3, right? Yeah, that v1 is in fact there. So it's just v1 power 1 minus gamma, and then the terms of v1 again. That is not good. So 1 minus gamma in v1, and then v3 power gamma minus 1. Damn, this is just really unnecessary stuff going on with it. So if I had to do this dimensionally, just v2 upon v1, and then you would just have, so v0 upon, right? So that whole thing could actually go there. I get it. So that v0 thing is okay. So this is 1 minus gamma over there, right? And then that would be 2 minus gamma. So it's just v naught upon, so v1, let's just say v1 upon v naught to the power of gamma minus 2 essentially. I guess, yeah, that would be the thing. Just to be sure. Yeah, it looks correct. Yes, it is actually in fact very much correct. So just 2 minus gamma for v1 upon v0. So this was slightly messed up, I suppose. And then essentially what you discuss is like v3 is v2 times that. So then v3 upon v1 is another lost cause, like upon v1. I guess I messed up somewhere, but I don't know where I messed up exactly. So the actual equation should be something like v3 equal to v2, and then v1 upon v0 the power of 2 minus gamma upon gamma minus 1. Yeah, that's actually the real equation. So essentially just have natural log of v3 upon v2 is equal to that stuff. Now what you have is natural log of v3 upon v1, which isn't very nice, but that could sort of be written like that. So fine, this just gives us 2 minus gamma upon gamma minus 1, and the natural log of v1 upon v0. Are we using v1 upon v0 anywhere? Yeah, we are using a lot of cases. First of all, just erase all of this because we kind of don't need this thing. Okay, and now time for like doing stuff the correct way. So you want to write this equation, so using that you can say that natural log of v3 upon v1, because that's what we really want. That is just the natural log of v3 upon v2 plus v2 upon v1, natural log of v2 upon v1 or v2 upon v0. Okay, you will have 3 terms. That's not very nice. But in any case, you just have v3 being something, right? So that's okay. So it's just natural log of v2 upon, in the end we're just writing everything using v0, v1, v2. That's okay. So v2 upon v1, and then plus this stuff. So it's just plus 2 minus gamma upon gamma minus 1, natural log of v1 upon v0. That's what we'll be using. So just copy that and paste it in place of this. Okay, I guess we'll need more space. This time solve v naught upon v1 power gamma minus 2 upon natural log of v naught upon. We should probably be changing this. I wish there was a better way. Come on, is there really just no better way? v naught upon v0. Oh, there is. Because this whole thing, you see, you can write it as natural log of v2 upon v0, and then plus natural log of v0 upon v1. But that's just essentially just minus of natural log of v1 upon v0. But then you can use that and then include it over here. So that minus 1, this thing just gives us 3 minus 2 gamma upon gamma minus 1 over there. So this would just be 3 minus 2 gamma upon gamma minus 1, and now you can just convert this whole thing as v2 upon v0. Cool. Yeah, that makes perfect sense. and now you can use that. So just like 1 plus p naught upon p1 power gamma minus 2, and this just becomes 1 plus this factor 3 minus 2 gamma upon gamma minus 1 natural log of v1 upon v naught. God, this is complicated, isn't it? We wanted to prove the efficiency is something, right? This is just it's just necessary at best. What if there was a negative over there? It wouldn't really change anything. This whole thing though, yeah, this whole thing is just really just messed up. Okay, let's just actually look at what 1 minus TC upon ds should be. So 1 minus TC, well, TC you can just sort of think of being, okay, I guess I just have to. So I was not expecting it to be this problematic. What's TC? TC thing is just this, right? So it's just P naught V naught, and TH is this thing, right? Amazing. Okay, think about it. Am I doing something wrong? No, I mean obviously this is a hotter temperature, right? And QH is taken at the hotter temperature, obviously. So how is it that the volume is increasing in that case? It's doing a reverse thing. So whatever, just stop thinking and doing it, right? Okay, so what's it going to be? So just 1 minus TC. TC is this stuff. So just, yeah, so just P naught, and then V naught upon V1, the power of 1 minus gamma. What? Okay, power of gamma minus actually. Minus 1, and then V1, okay, upon, so this is the thing, P naught upon V naught. No, okay, it should be the reverse of this. This is the colder one, this is the hotter one, right? So just P naught upon V naught, this cancels, just get this thing. It's 1 minus of this stuff. Well, apparently we didn't even get a minus, so what should I say? This is just messed up, isn't it? Yeah, it sure is. Oh, I guess this term should really just have been 0, but it wasn't 0 for some reason. What was in there? That term. I'm getting sort of, tired of doing this whole thing actually. It's just natural log of V2 upon V. Okay, wait, where is that one natural log going? This doesn't make sense, right? Okay, so it should be upon natural log of V2 upon V0. Okay, that's fine. Now we just need to figure out what these guys are going to be. Oh, come on. No, something is just wrong. Something is extremely wrong, but I cannot get what's wrong. Like, this term should just be 0. It is not, for some reason. I even lost count of what I was doing. So we were essentially stuck on this part, right? The V1 upon V naught. Okay, so that part was like used up in any case because this was used in gamma, right? So this should have been natural log of V2 upon V naught, and this also should have been natural log of. So really, this only makes sense if you actually have V3 upon V1 being exactly equal to V2 upon V0. This is only condition when this actually makes sense. But is that true? V3 upon V1 equal to sorry, that happens. Is this true? On V2 upon V0, going from there and going from there, right? I don't know. just really don't know. So you have V3 as, yeah, using this equation, but it doesn't give me anything, does it? PV power gamma, V power gamma over there, yes, that's okay, but just V1 upon gamma minus 1, how is that even making sense? V3 upon V1, that should be this. This should not be 1 then in that case. What the? No, something is wrong. What is wrong though? Should we just start over? So essentially our whole idea boils down to having this sort of a thing, right? That V3 upon V1 is V2 upon V0. Now how do we go around proving this? So once again, 3 is this thing and 2 is that and 1 is this thing and V0 is that, right? Temperature, go to B. Look, these are adiabats and this is an isotherm. Okay, fine. So this is still complicated. So what do we know? We know that the energy transitions should be the same. So essentially the temperature changes, that should be the same, but we already know that obviously because the temperatures are the same. So that's not very helpful. Okay, let's just write down all our equations again and see if anything nice comes out. So we just have P0 V0, P2 V2, then P1 V1, and then P4 V4. Okay, so let's just try to write down some stuff. So we know that this was an isotherm, this was an isotherm, this was an adiabat. Okay, sorry, this is an isotherm, just T1, T2, whatever, and then these two are adiabats, right? Okay, cool. So since these two are adiabats, you have these important equations: P2 power V2 power, so V2 equal to P4 V4. It should just be 3 over there. Okay, so it should just be P3 V3, whatever. Then P0 V0 equal to P1 V1, but using these, okay, sorry, these are isotherms. What am I doing? So P2 V2 equal to P0 V0, fine. And then P3 V3 equal to P1 V1, sure. But you also from that have that P2 V2. Oh, I see what should have been done, and I was not doing it for such a long time. Okay, fine, I get it. Look, divide this by that whole equation, divide this by, and that essentially gives you that V3 upon V2 is equal to V, right? Obviously, and from there, if you have that, yeah, this whole thing is just stupid. This whole thing is just really just stupid. Like, come on. Really? So if you have that, then this V3 upon V1 term just becomes V2 upon V0, and then you can just sort of cancel this away. And yeah, wow, amazing. And so we just get something like, okay, V3 upon V1 is actually like no, it's not V2 upon V0, is it? So V3 upon V1 is like going from there to there. So okay, that's weird. The heat transfer during this isotherm, so to the gas, what's that? And the work done by this, oh, it should be negative over there, right? Oh, that also makes sense why we're getting some wrong answers, because this should have been negative over there. No wonder. So yeah, okay, that's the way it's done. Fine. So what we essentially show is that first your V2 upon V0 equal to V3 upon V1, and from there everything follows easily. So A part is done. Let's go to the B part. Show that for an arbitrary gas with extensive parameter Vn, fixed for now, the specific heat is given by this thing. Okay, so they are saying Cp minus Cv is equal to Vt alpha p power square, okay, alpha p squared upon Kt, and this is for an arbitrary gas, right? Not necessarily for an ideal gas. And where we have alpha p is equal to 1 upon v partial v by partial t at constant pressure, and then Kt is minus 1 upon v partial v by partial p at constant temperature. Yes, there's quite a bit of weird stuff going on, but whatever. Also, we obviously know that Cp is just the heat capacity at constant pressure. It's just basically like um, at reversible constant pressure situations. So it's essentially just partial. I shouldn't say Q, that would be weird, but okay. So since it's at constant pressure, what can we say? We can say it's like dE minus so dE plus PdV, right? That's one way to be seeing it. Heat capacity at constant pressure. Well, you can always write it as that. So it's partial by partial temperature at constant pressure, right? Of, so basically like the enthalpy, which is just energy minus PV, sorry, plus PV. But yeah, the reason is because we are talking about TDS essentially, and then CV is just partial upon partial T of energy at constant volume, right? So these are the relations that we sort of want to use. So once again, these are just like saying TDS upon dt, yeah, constant pressure. Wait, can't we just use that directly? Yeah, we don't even need to go to the energy stuff. So we can just say that Cp is just T partial S by partial T at constant pressure, and this is just T partial S by partial T at constant volume. Why would go to energy and enthalpy and all that? Just do this. This is just so much better, isn't it? Yeah, so essentially what we sort of want to prove is partial S by partial T at constant pressure minus partial S by partial T at constant volume, that's equal to V and all of this stuff. So alpha P is this 1 by V square, okay, and Kt will have a negative 1 by V, so this whole thing could just be taken as negative, and so just that V just cancels essentially. So just have alpha P squared, so it's just this thing, okay, and then upon Kt, so it's partial V by partial P at constant temperature. Now this thing is, by the way, at constant pressure, isn't it? It's a constant pressure, right? And this whole thing just becomes partial P by partial V at constant temperature, because obviously you can do that. Yes, you can do that. Don't doubt me. We can certainly do this. Once again, the usual thing that we do is like bring everything to one condition, and then everything works out, right? So let's just say we want to bring everything to constant temperature, so we want to find what this would be under constant temperature, if that makes sense. So I guess that would be something like partial P by partial S at constant temperature. No, something is really wrong. No, this isn't right. This just isn't right. It should not be like that. But we do want to prove this, don't we? Yeah. Well, think about it. So what we also need to prove is this stuff. Okay, so use Helmholtz representation. Entropy is a function of temperature and pressure. Okay, so we don't want at constant volume, we want at constant pressure, isn't it? Okay, so we would like to not have this thing. Now I don't like this temperature over there. This is sort of bugging me. Can't we just convert it to something else? I guess we can. So first what we can do is center constant volume, right? Okay, that's amazing. Constant volume. I want to be writing it something else. We don't like entropy, right? We don't like entropy, but you never come across a term like that, do you? No, I've never come across a term like this. Okay, so let's just write out all the terms that do include entropy. So you know that you can just write dE is equal to TdS minus minus PdV, and yeah, so you just take the partial derivatives with x and y, so just like partial square. So once again, I'm just going to that usual equation. So partial square E upon partial x square, that's just a bunch of terms. Yes, I know. We just have t partial square s by partial, so partial x partial y, by the way, partial x partial y. Then you just have plus partial t by partial x, partial s by partial y, minus, so a lot of other stuff. So that's just minus. So I'm just gonna write down the whole thing directly. So just partial t by partial x, partial s by partial y, minus partial p by partial x, partial v by partial y. This is just equal to partial t by partial y, partial s by partial x, minus partial p by partial y, partial v by partial x. Once again, cool. So now we're thinking of this thing. Okay, I bet it would make sense to be converting these terms first. Either we could convert everything just entropy and pressure and temperature, which I guess is actually sort of better. So we sort of want to eliminate these v terms essentially, right? So every term where you have this v factor coming in is what you want to erase. Cool. So you want to find what partial v upon partial t is under constant pressure. So that would essentially mean we want a constant temperature, constant pressure situation. And so doing that, which is that's not good. Think about it though. Can you ever have a constant temperature situation? You cannot. That's bad, isn't it? Yeah, that's bad enough already. A constant pressure. Okay. Well, you gotta think about it. Yes, this is in fact just the case, isn't it? So, yeah, a constant pressure and a constant volume. Oh, come on, think about it. Written that. What can you write though? You can also write this thing. So everything's a function of temperature at this point, right? So partial is upon partial t. Well, so then you can use the chain rule a bunch of times and just say that, oh well, then volume is also a function of temperature. So it's just partial s by partial v by partial t, and this whole thing is at constant pressure, constant pressure. So now, can we get this term? Well, we can actually. That was not bad. And then minus, so just have this stuff. So once again, that is a constant of volume, so we can put the pressure thing over there. So it's just minus partial s upon partial p at constant volume, and then partial p upon partial t at constant volume. Interesting. And that's equal to this stuff, right? Minus partial v by partial t at constant pressure squared, partial p by partial v, and then at constant temperature. So okay, that's giving me a ray of hope. Yeah, I bet we can sort of deal with this now, because we can just substitute whatever this stuff is to get stuff that we want. So we just need to be able to kill this constant entropy situation, right? Yeah. So how do you find partial s upon partial v at constant pressure? Well, put pressure and volume as the terms, right? So what do you get? So putting pressure and volume as the terms, you would just have some stuff cancelled. Yeah, this is actually gonna work. So just put x equal to pressure and y equal to the volume. So then you just have partial t by partial p at constant volume, and then partial s by partial v. So once again, x equal to p, y equal to v, right? Cool. At constant pressure, this whole term dies because, well, x is p, so this thing is 1. partial v by partial, oh that's just minus 1 over there, fine. This thing is equal to, so what survives over there? Well, partial is a partial, so that survives, and then partial p by partial y dies, this whole term dies. So this just gives us partial t by partial p at constant pressure, sorry, wait, this is wrong, at constant, yeah, that's the thing. And just have partial s by partial, yeah, this is okay, okay, partial, what is it called though? Yeah, what was I doing really? Kind of forward, yeah. Partial p at constant volume. This looks awfully familiar to something. Yep, it does. Obviously it does. So look at this stuff. What is this? So you just have partial s upon partial v at constant pressure, partial v by partial t at constant pressure. That's slightly different though. Huh. I wonder how that would. Oh, it makes sense somehow. So if I were to put that over there, that's a negative. This becomes equal to 1. Yes, I sort of get it. Yeah, just sort of, but it's not too bad. Okay, so I'm just gonna copy this equation, the thing that we want to prove. Just like squeeze all of this. So first what I can do is just divide by this guy's reciprocal everywhere, so it just becomes partial s of partial v at constant pressure, and simultaneously, you know what, okay, let's not do stuff simultaneously, that leads to problems down the line. So just partial p by partial t at constant volume, partial t by partial v at constant pressure, and that's equal to, so this just is minus partial v upon partial t at constant pressure, and then partial p by partial v at constant temperature. Yeah, and so to match it with this stuff, so you need a partial t by partial p term. So if you add that, you just get partial is a partial v at constant pressure, partial t by partial p at constant volume, and that term is essentially coming from here, so you basically multiply with the reciprocal. So just minus partial s by partial p at constant volume, partial t by partial v at constant pressure. Right, what is that quantity, by the way? It's just 1. So what you're basically saying, I deleted some stuff which wasn't supposed to be deleted. So you are essentially saying that 1 equal to minus of partial v by partial t at constant pressure, partial p by partial v at constant temperature, and then the reciprocal of this term, which is just partial t by partial p at constant volume, and that's exactly the chain identity they call it. And we want to prove this true. Wow. So I'm just gonna write this again, so in like better handwriting. So what we have is this thing, right, at constant temperature equal to -1. Now how do we show this? Well, we can use this equation again and again and again, and that will give us what we want. So first, we want something which has a temperature and volume dependence. So like, how do we get that? It's one thing we can do. So I just want everything to be done in like one variable, sort of, right? So this is like constant temperature, everything. So this thing we can sort of convert to a constant temperature situation by, and this thing we can convert to a constant pressure, constant volume situation, and this we can convert to, it's already in constant temperature situation. That's not a good idea. Yeah. Oh, so what we'll have to do is like we want to take the reciprocal of that, because in that case we would be able to convert that, right? So the equation that we really want to work on is not this but this. And how am I getting all of this? Just like work through this stuff and you'll understand what I understand now. But yeah, so you see T and V over there, right? So we sort of want to use that, right? So we want like, so just take constant temperature, just take temperature and volume as x and y, and let's just see what happens. So let's just say x equal to T and y equal to volume, and put that in this thing. So it's just, the first term is just 1, and then this stuff, so partial s upon, so the y term is just becomes v, right? So upon partial v at constant temperature minus this stuff, so partial v by partial y, that's just 1 over there. Okay, cool. And everything over here is just messed up because yeah, it cancels, so just get equal to, and then this stuff, partial p by partial x, which is partial p by partial temperature at constant volume. Cool. And this is what we wanted, so we can just put this in there. And now let's also put x equal to T and y equal to pressure, and let's see what we get. So once again, partial s by partial p at constant temperature, like this term just, it just like vanishes. T by y, that is also going to vanish. You just have minus partial v by partial x, x is T, so this term at constant pressure, and this is the term that we wanted, so just put that in there, or like put this in there, right? So what are you getting? And that negative cancels, by the way. So what you essentially get is like partial s by partial v at constant temperature times partial s by partial, something is messed up. Oh sorry, it's this term, it's yeah, it happens, the wrong direction, right? This is where I should be putting it. Okay, cool. So essentially what you get is like partial s by partial v at constant temperature times partial v by partial p at constant temperature, that's equal to partial s by partial p at constant temperature, which is just the chain rule, so that is obviously true. And so yeah, we have sort of proved that Cp minus Cv is just Vt alpha p square upon Kt, which is, it's a mouthful, but let's just move on. Let's go to C. So yeah, we don't need any of this anymore. Should find a faster way. Okay. So let's just go to the C thing, which is, so entropy expression for an ideal gas. So we want to use the Euler relation. So basically just this thing, that dE equal to TdS minus PdV, and then figure out an expression for entropy. Okay, cool. So this is for reversible processes, like all sorts of reversible processes. Now you have this equation of state that PV is equal to, so this is sort of weird, but they have written C over there. Okay, that's a mistake. That's a mistake that they have done. But anyway, just have PV equal to NKBT, and the energy is C times KBT, and in this case C is 3/2 for a monatomic gas. Okay, so we want to integrate the Gibbs. I'm not caring about hints anymore. I'm just gonna plug stuff in and just see what happens. Yeah, so we want to find S as a function of temperature and volume, just my choice of variables. So first, we don't like P, so eliminate P. So P is what? P is just NKBT upon V, right? So just sort of, take its derivative, just have D. We don't even want to take the derivative, just put that in. And TDS is okay. What is DE? DE is just CKBT, I suppose. I'm just gonna put an N over there because they have somehow missed it. It should be there. Yeah. Damn, they really just start doing mistakes, aren't they? Why did they? Is it supposed to be a trick question? Like, you actually have to work with these equations? Because this doesn't even make sense. Like, how can C just... So what they have written down is like E equal to C KBT, which is just stupid because then energy is not an extensive variable. but I guess, yeah, that's just a mistake most likely, so I'm just gonna go with this. Right, so what you have is E equal to wow, it's been 1 hour and I've done 3 questions. Okay, just keep going. So E equal to C N KBT. Now what? Just put that in. So DE just becomes Cn KB dt, that's equal to TDS minus PdV, just this stuff. So NKBT upon V and then dV. Amazing. Right, so what do you have? The T stuff just goes like ds is just, so put that stuff over there, so just basically like nkb upon, so nkb dv upon v, and then that t thing denominator, so it just becomes plus c nkb dt upon t. Amazing. Right, so from there you can sort of easily see that s is just nkb because that's sort of just constant. Natural log of v t power f by 2 upon obviously like v naught t naught power f by 2, because some base thing, whatever. Sorry, I shouldn't say f by 2, I should just say c, but I'm used to f by 2, so fine, just put c over there. That's the thing. And if you want a more rigorous thing, just like use partial differentiation and all that, but this is okay. The total differential is something that I do deal with, so it's okay. Next, the first question, that whole adiabatic and isothermic thing, that was yeah, that really just took a lot of time, didn't it? It did. Okay. Consider a gas system adiabatically isolated with subsystems at equilibrium, separated initially by an adiabatic wall with thermodynamic coordinates, this respectively. Okay, so just you have a container V1 P1 naught. What the? Okay, fine. I'm just gonna write like that. And then N1 and V2 T2 not N2. So fine. And this is a gas system adiabatically isolated, so this whole thing is no heat flow, so this is adiabatic, and this thing is this is a diathermic. Fine. If the adiabatic wall is quasi-statically allowed to become diathermic, wait, what? Subsystems at equal, so okay, this is also adiabatic, sorry. So just have this, fine. So now first question is, if the adiabatic wall is quasi-statically allowed to become diathermic and the system is allowed to exchange heat, you want to show that the entropy increase is delta S is just the integration from T1 to Tf C1 T1 dt upon T plus God, what the, where C is the heat capacity at constant volume of the ith part. What is the, oh okay, so it's just 2 parts in fact. Tf is the final equilibrium temperature. It's okay, I get it. Okay, write down a formal equation that determines Tf. This is sort of automatic. So is this process reversible? It's not, obviously. It isn't. Then is this equation of Ts equal to integration of dq reversible upon temperature even going to work? I don't know. I really just don't know. But the only way I could show this is using this equation. Okay. Come on, just think about it. What do you know? What do you know about this? So it's not a reversible process. Fine. And then you want to show that the heat, that the entropy exchange is exactly that. So what they have written down is that delta S is just integration from T10 to Tf. I'm just actually going to write this as T1, not T10, because it's just painful to write more subscripts than I should. Then the heat capacity of the first guy, T1, as a function of T1, that is. Yes, I get this. I get what you're doing. I get that you are basically just, yeah, I get it, but it's not a reversible process in the first place. So how come that you can actually do this thing? Yeah, this ain't a reversible process. A formal equation that determines TF. So once again, what sort of system is this? Gas system. Okay. So you are not even having the pressure thing in there, do you? No, you don't. Why is this actually reversible somehow? Oh, because it's an... Okay, so let's just assume that these are ideal gases. Right, okay, then all of it just makes sense, doesn't it? Yeah, it does. Right. Because if these are, what do you call it? What was I going to say? Right, if these are ideal gases, then, there is no work done. So then this whole thing is just the increase in energy. So essentially what you're writing is like integration of dE upon T, right? Under constant. Yeah. Yeah, and oh, okay. I get it. I really just get it. In this particular case, although it's not a reversible process, you can sort of write this. Wow. I was not expecting this. I mean, I really just was not expecting this, but it's okay. I guess it's actually right to write it like that, because you see that dE can actually just be written as partial. So you know that partial E by partial S is just what temperature is or something. So since at constant volume, and since this is a constant volume situation, like throughout, I can just say like dE equal to TdS directly, and so just putting that over there, what you essentially have is just ds, integrating that. Okay, so apparently ds is equal to, yeah, okay, amazing. This is messed up at multiple levels, but somehow it's working. Yes, it's not a reversible process, and still it's working. I don't know what I should be saying, but okay, it doesn't even have to do with the fact that it's an ideal gas. It just is, sort of. What? Why? But this should not, right? Why is this? The heat capacity is just that. Obviously, there is no work done on this thing, so that's, yeah. So the heat capacity at constant volume just becomes like partial E by partial V at constant. Sorry, partial E by partial T at constant volume. That's what the heat capacity is, and that times of dt. Yeah. So you wanna somehow get this. God. Okay. So that's just dE over there, isn't it? Yeah. So. Okay. If you can show that this whole thing, just becomes equal to ds, then you are essentially done, right? Yes. Yeah. Or if you can show that this is the thing at dt at constant temperature, so at constant volume. So essentially what you're saying is like dE upon dt is just equal to T times of ds upon dt at constant volume. If you can show that, then you're done. But that's obviously true, because dE equal to TdS minus PdV. So At constant volume, obviously just have, oh, this is weird, very what do I say, fine, I guess it's okay, yeah. So at constant volume you obviously just have d equal to TdS and then divided by dt. It's okay, it works. Heck, and this equation is valid for any two states which are in equilibrium. You can do this ds calculation and then do this thing, right? And since we're doing it quasi-statically, this equation is like valid for even this process, and so you can just somehow show that this is working, although it's not a reversal process. Wow, I am really just dumbfounded by this fact that I've learned today. Okay, fine, so that somehow works. And now what do we have? God, okay, so now what we have is that you know, okay, C1 changes with respect to the temperature, obviously. And you want to find what F is as well. So TF is the heat capacity at constant volume. Let's changing this to temperature, obviously. So just assume it's an ideal gas first. If you assume it's an ideal gas, what do you get? So you just get like the heat capacity at constant temperature. That's just the, what is that? It's like, that's CV, right? Yeah, or more like NCV, but whatever. So that's just PV plus RT. Yes. So just like 3 upon 2 or F upon 2, change in that. So just 3 upon 2, sorry, F upon 2 again. So F upon 2 NKB, and then we have delta T. So this is the thing. That's what this C thing is. Just have TT over there. So once again, what we can see is like it's F1 upon 2 basically, dt1 upon T1. It's going from T1 0 to TF, and that's equal to, so from T2 0 to TF, C2 of, so C2 is just this thing, right? F upon, so F2 by 2 N KB dt2 upon T2. So this stuff obviously just cancels. So you just have F1 natural log of T0 upon T1 naught. Okay, this is a bad, this should be T final over there. T final, I'm just gonna call it T1, right? So T1 is equal to F2 natural log of T final upon T2, right? This seems to be correct. So essentially what we're seeing is like TF power F1 minus F2, that's equal to T1 power F1 upon T2 power F2. So just TF is equal to T1 power F1 T2 power negative F2, that whole thing. So just that whole thing to the power of 1 upon F1 minus F2, and that's the thing. That's your final expression that you want. So the second A part is also just done. We can in fact just write down the final expression directly. You just have TF is equal to T1 power F1 T2 power minus F2, all of that to the power of 1 upon F1 minus F2. Amazing. Next thing is B. Okay, so using heat capacity, whatever, show explicitly that delta S is bigger than 0 in this process, is i.e. irreversible. Okay, so using, oh, okay, for a monoatomic ideal gas. Interesting. So if your heat capacities are, both of them are in fact like just 3 by 2 kV, as in they're equal, then what you would have is that your T final would just be, T1 upon T2 to the power of F, and then this, oh, this thing is problematic, isn't it? Yeah. Okay, I want to show that delta S is bigger than 0. Wait, what? Okay, so this could be a reversal process apparently. It's not necessarily, but it could be. This is very weird what we are doing right now. Oof. Look, there's also this whole thing that integration of, so by conservation of energy, what you should probably have is that this thing, right? So like T1 to TF, this should, I guess, just be equal to integration from T2 to TF, C2 T2 dt2, right? That's kind of a requirement, isn't it? Is it not? I messed up somewhere, did I not? Yes, I did. How did I find this TF again? Yeah, how did I? Oh, god damn it. Sorry. This should not be the case. This is wrong. I assume that delta is, it can't be. It's not reversible. So, I'm just sorry. Okay, so this should be different. It should be that F1. God. So it's like F1 TF minus T1 is equal to F2 TF minus T2. That's the that's how it should have been. I just feel really stupid right now. So this TF is equal to what? T1 F1 minus. This is like basic stuff. Why am I even spending so much time in this? It's just, I'm just really slow right now. Okay, that's the thing. Now delta S is proportional. I'm just gonna write it directly. It's proportional to. I'm just gonna write it like that. Delta S is proportional to. So there was natural log, right? So just natural log of. So you had an F1 over there. So just proportional to F1 natural log of T final upon T1 minus F2 natural log of T final upon T2, right? I should be plus, I guess. Yeah, right. That's how it should be. So now if so if you have different T values and you sort of have the same, also this should be plus over there, right? This too. Yeah, right, it should be plus, this is equal to 0. That's why this should be like that, right? Common logic. Anyway, that aside, the thing is, you want to write down formulation for TF, but that's done. Now what else was I supposed to show? Right, so if C I and so if C1 C2 are both 3/2 kb, then you want to show that delta S is bigger than 0, right? Okay, so just calculate what delta S is, right? It's proportional to this guy times some positive constant, obviously. So since your T1 T2 are different, well, your TF will obviously be like in somewhere in between and whatever. For this thing to not be 1, well, that's okay. So for this to be positive, what we essentially want is like natural log of that should be positive, which is to say that TF square upon T1 T2, that should be bigger than 1. So like TF square should be bigger than T1 T2. Okay, that's fine, but you know that T1 plus T2 upon 2 in this, because F1 and F2 are the same, is what TF is, but we already know that TF is then in that case is bigger than or equal to, because AMG inequality, the square root of T1 T2, but that means TF squared is bigger than or equal to T1 T2, but that is right, that is exactly just the situation that delta S is bigger than 0. So we have showed that it is in fact happening. So B part is done. So to the C part, there is no C part. Fine. This is question number 3. Yes, I know I'm taking too long. Fine. Consider a gas enclosed in a cylinder with movable piston. If walls are adiabatic, a quasi-static increase in the volume results in the decrease of pressure according to PV power something constant. Okay, so PV power 5/3. It's constant. Consider the following PV diagram. Whatever. PV power adiabatic. Cool. Fine. Calculate the quasi work done in always the adiabat. along the adiabat. Fine. Calculate the heat in the process using the previous step. Oh, so they want to find the work done on the system in an adiabatic process in the first place. Well, that's just change in energy, right? So the heat in the process ACD and ADB and AB. Okay, the heat. Well, fine. So delta E thing is just the same, right? Yeah. I guess I'll just do it. So let's just go with the diagram first. So what they have is that they've been given a bunch of processes between two states A and B. One process is an adiabat, and okay, A is, so it's a PV diagram that we're talking about. A is having pressure 10 power 5. This thing is, what is this? Okay, it's 8. It's 8 times 10 power minus 3. This quantity is 10 power minus 3. This quantity is what? 10 power 5 divided by 32. What? It's extremely weird. I don't know what that thing is, but fine. 1 upon 30 times 10 power 5. Is that division? I think it's division. Anyway, just some weird thing that they have written down. So you have a bunch of processes. One is an adiabat going from there to there. This is like a two-step process that's going like that. You have this line. Yeah, I'm not gonna talk about this, whatever this process means. And you have this process going like that. What do they want? First, that they want is calculate the quasi-static work done in the system along the adiabat. So this adiabat is, by the way, given as PV power 5 by 3 equal to constant. So gamma is just that. Fine. So we want the work done on the system, by the way. So that's just the change in energy at this point along the adiabat, right? So you know what that thing is going to be, right? It's just the change in energy. So that just yeah, so that just the degree of freedom is obviously just 5, so just 5 by, should be 5 by, why is this, oh it's 5 by 3. That is problematic, isn't it? But still, it's just a change in energy, right? So if we can find the degrees of freedom, we would essentially be done. So you know that gamma is just F upon F. That's problematic, isn't it? So the kind of system that we're dealing with is a gas enclosed in cylinder and nothing else is given. Not good. Okay, so this can't be done in the usual procedure. Okay, let's go with a different route. So adiabatic process, dq is 0. So the work done is just the change in energy. Sure, but okay, this is not going good. And this is the thing. Fine. Let's just have dE equal to minus PdV. So we just want to find a change in energy, right? Yes. Or you can just directly find the work done, throughout the thing. So just the work done, which is also the change in energy. The work done on the gas, obviously. That's equal to just the integration of negative PdV. P1 to P2, whatever the thing is. I'm just gonna actually not write this down. Just negative integration of so now P is, oh god, it's given like that, right? Just call this P0 V0 to P1 V1, whatever. Yeah. So now okay, so just have this thing, PV power 5 by 3. So that's just P0 V0 is equal to PV power 5 by 3, right? So pressure is just given as P0 V power negative 5 by 3 V0 power 5 by 3 dV. Yeah, which is what? So let's just integrate that. So it's going to be minus 2 by 3 divided by that, just 3 by 2. So 3 by 2 integration. Fine, so just P upon V power not power 5 by 3, and it's got V power 2 by 3. I suppose that's wrong. Okay, that's wrong. So just V0 power 5 by 3, and it's got V power minus 2 by 3. It's going from this to that, so just V0 to V1 or whatever. Okay. This is kind of weird, isn't it? I don't even know if this is actually making sense. Show 1 is to power 5. This thing is. Yeah, this power 3 is like 1 power 3 and then. So 1 by 32 power 5. That is equal to. What the hell is this? Just really, really weird. Oh, that's actually supposed to be power 3. So it's 1 by 32 power 3. That's equal to. Okay, that's volume. So it's 8 power 5 upon 32 power 3. That's fine. It works. It works somehow. Anyway, this is what we kind of want, right? So this should be, I guess, P naught V naught over there, right? Yeah, okay. So just 3 by 2 P naught. Oh wait, what is P naught? That's that constant, whatever that particular constant is. We don't care actually at this point. So just P naught V naught power 5 by 3. Yeah. And this is just the thing. This is so V power minus 2 by 3, right? Just like, isn't there some better way to be doing this stuff? Who cares? Just 1 upon V power 2 by 3. So V1 and then minus 1 upon V naught power 2 by 3. Alright, so let's just start putting this stuff. This can also be sort of written in different ways, which is like P naught and then you just got this stuff. So V naught power 5 upon V1 power 2 the power of 1 by 3 minus this whole thing, just V naught basically. So that's what 3 by 2. Instead of P naught they have given us 10 power 5. Okay, what's V naught? V naught is 10 power negative 3. So that's 10 power negative 15 upon V1. V1 is 10 power 5 upon 32. So it's going to be 32 squared. And this is 10 power. This doesn't even make sense. Oh, that's pressure. Sorry, that's actually just pressure. This is wrong. So V1 is 8 times 10 power negative 3. Makes sense. So it's going to be 64 times 10 power negative 6. That power 1 by 3 minus V naught again. So that's just 10 power minus 3. There you go, that's the thing. So it's just be equal to what? 3 by 2 times 10 power 5. And this thing. So 64 cube root is just what? 4. It's just 1 by 4. And this is what? Minus 9. It's just minus 3. Left minus 1 is like what? This is just minus this negative of 3 by 2 times of 3 by 4 just to the power 2. And this thing just like minus 9 by 8 times of it's kind of like minus whatever, so just minus 3 times of 25 upon 2. That's the thing, which is like minus 75 upon 2, which is just minus 35, and 25 is like what? 375. So minus 37.5. So it's minus 37.5. So this whole thing is just minus 37.5. What is the unit? Unit is what? Pressure is in Pascal and this is in meter cube. That's the SI unit, right? Oh, this is SI unit, just in joules in that case. It's minus 3.37.5 joules. Cool. So that's part A. So minus 37.5 joules in this whole process. Because obviously the volume was pushed down, so the work done on that's supposed to be positive, right? Yeah. Oh, I missed this negative sign, didn't I? So it should be positive, right? Yeah, so it should just be positive. This. Okay, B is a small pedal is installed inside the system and it's driven by an external motor by means of a magnetic what is this? I don't know. Magnetic coupling through the cylinder wall. Whatever. I don't even understand what the description is. The motor exerts a torque drive the pedal at an angular velocity. I'll just try to draw this first of all. So they're saying a small pedal inside a system driven by an external motor by means of magnetic coupling. Fine. Through the cylinder wall. Fine. The motor exerts a torque driving the pedal at an angular velocity omega, and the pressure of the gas at constant volume is observed to increase. What gas? System. External motor. But where's the gas? No gas, right? Pressure of the gas at constant volume is observed to increase at a rate of fine. So it's this equation that we will given dv by dt is equal to 2/3 omega upon v times torque. I don't quite understand what's going on exactly. Show that the energy difference between any two states of equal volume can be determined with this particular calculate. What is going on? Well, this is a 4-part question. I better start to understand what's going on. Oh, by the way, the A part thing is actually not done yet. We also have to answer 2 more questions, in fact, for the A part to be over. So we also kind of want to find the heat in the processes ATB and ACB. Okay, the heat obviously. Cool. So in the adiabatic process, the heat was 0. In this case, it's not 0. So A to D, the pressure is constant. So the heat is just a change in enthalpy. We can't do that. It's not an ideal gas anymore, unfortunately. Oof. So we'll have to go the no, but that still works, right? It's just a change in enthalpy. Yeah. So we did not use temperature in the last case, did we? No, we didn't. So find a change in enthalpy. It's not that bad, is it? We don't know an equation for entropy, so that is problematic. We kind of only know the idea that. Just think about it though. What do we know? Well, you know it's constant pressure, so the work done you do know. The energy change you don't. Oh, but you can find it because we were given the adiabatic isotherm, and that kind of gives us the energy changes, right? Yeah, so the full energy change you do know. What about the full work done during this procedure? You also know that. So this is also just the energy that we gain during the whole process, right? Okay, so now once again I'm going to draw the plot. So now what we want to do is, for these processes, we want to find the heat input, sorry, the work input, right? Because then what we can do is just subtract it from the energy, and then it's gonna give us the heat. Cool. So what's the work done in this? 0. This is 0. But what about this? So it's just P times V, delta V. So that's 7 times 10 power negative 3 times 10 power 5, which is 700 joules. What? Okay, that is some quantity. 700 joules. That's very fine. Okay, for whatever. 700 joules. This was 37.5 joules. How come? Okay, let's no, this should not be the case. Okay, this is the work done, isn't it? Or here what we wanted was the work done again. So then work should be somewhere in between, but that's not what happened. Did I mess up while calculating the work for this thing? I guess I did. So it's just integration of PdV, right? Negative whatever. So that just 5 by 3 is equal to constant, right? Okay. So what's the pressure in that case? It's just V naught power 5 by 3, and then you just got V power 5 negative 5 by 3, right? And then dV, and that's just the thing, integration from V1 to whatever. I must have messed up somewhere. There can't be any other thing. So just the P naught thing is just 10 power 5, it's out. Then you also have the V naught thing, which is kind of already given to us, just 10 power negative 3, the power of this guy. So just 10 power negative 5 essentially. That just cancels with this thing. So just the integration of this guy, right, which is 2 by 3, that negative cancels, so just 3 by 2 essentially. Yes, and then v power 2 by 3. It's going from something to something. Well, the new thing is just 8 times 10 power negative 3, so it should be, that's a positive quantity, isn't it? Well, it's okay. The volume increased, so like the body did work outside, so the work done on it was negative. What the? Okay. Yes, your volume certainly increased. So the work done on the body was negative. It should be negative over there, right? We want the work done on the system, so this is negative obviously. Okay, so you got 3 by 2, and then this thing is, why am I so slow right now? Right, it's just v power minus 5 by 3 that's equals 2 by 3, and that's just v power minus 2 by 3 going from what the initial value is 10 power 3, it's negative 3, and then this is 8 times 10 power negative 3, so yeah, so it's 3 by 2, and then you just got, just put that thing in there. Is that 10 power negative, so that 1/3 part is 10 power negative 1, negative of that, that's 10 power 1 but square, so just 100, so 100 times this stuff, and it's now just 8, so 1 upon 4 minus 1, so just 3/4 negative. That is the thing, and that is exactly what we went with, right? No, okay, it was slightly different, so it's 9 times 25 upon 2, right? We slightly messed up, very much, just slightly, but we did mess up, so it should actually just be 100 times 9 upon 8, yeah, which is, so it's like 1, and then we got a 10, which needs another 1, and then a point. Oh wait, just do this thing correctly, so 1.1, 10 and 8, and then 20, so 20 divided by 16, so just 2, and then a 40, so 5, so that's just this thing, so it's 112.5, not this. Okay, you also want the heat in the process ADB and ACB and AB. Okay, cool. Just find the work done throughout these procedures. Well, this is 700 joules, so the energy change is just well, yeah, the work done is just the energy change, right? So that's the thing. Although this should be negative PDV integration, so just negative of that, in fact, right? Yeah, so just negative of 700 joules. So just energy minus that, right? Which is just happening to be 700 minus 112.5 joules. It's like something, just 0.5 and 9. Sorry, so 9 minus was like 7. 9 minus 7 is like what's 8. This is 6 minus 1 is 5. So 5 is 87.5 joules. And lastly, you also want this thing. Yeah, so just now it's going to be what, like, it just the volume change is the same, the pressure is just 1 by 32 of that one, so it's 1 by 32 of 700 basically, so it's like 7 times of 25 upon 2 minus, so wait, no, okay, that's just 4 1, should also be that 8 minus 112.5, whatever that number is. I don't want to calculate this at this point. Oh, come on, let's calculate this thing. So it's just 7, it's like 14 35 is 175 upon 8 minus 112.5, which is what? It's negative, yes I know, but what is it? So this is 2, 16, 15 is like what, 1, and then 8, so 0.7, 70 requires 64 is 8, and then you got 60 once again, which requires 50, come on, what am I doing, 56, 7, 40, just 5, minus this guy, so just 112.5 minus 2, 1.875, and this is like what, 5, and then okay, what was I doing? Right, just 4, 9, and then you got a 10, isn't it? Yeah, cool. So 9 minus 7 is like what, 2 and 4, so 14 minus 8 is 6, and then this is 0 and 9, so this thing is just 90.5 is the negative of that. So negative 90.67 625, yeah, 625. Joules, all of these. So A part is done finally. So the B part is, oh, okay, that's ACD. Okay, wait a second. Okay, ADB, ACB, and AB. Oh, there's another part. So we also have to do the AB thing. I'm really just tired. Now it's a triangle, isn't it? Amazing. So we kind of know it's just going to be the average, right, of these two. Yeah, that now looks about right. So just the average of these two, isn't it? So it's the average of 8, so 587.5 minus 90.625 upon 2, obviously, but we'll do that later. So this gives us what? Or you know, just do it directly upon 2. So this is like 25 and 4 is 29, and this is 3 and the 0.5, but that's a 2, so it's just a 7, and then 75 minus this thing is 45.3, and then 1, and then 2 okay, so 2.5 over there. Cool, that's the thing. So 5, and then 9 is to 7, this is 4 and 3, 4 point, that's 3, I hope. Yeah, 8 8 plus 4, 2, 2, 4, 8 points, whatever, round it off to 2, 4, 8.5. No, not 5, I guess 4, 4 is better. It's 248.44 joules. Okay, so A is finally done. Let's go to B. B is a small paddle is installed inside the system, and it's driven by an external motor by the means of magnetic couple through the cylinder. Right, this whole thing. So once again, back to the equation: dB by dt equal to 2 by 3 omega upon V times torque. Show that exactly the energy difference between any two states of equal volumes can be determined by this process. So you know the pressure changes with time. The omega thing is constant, I suppose. Angular velocity, the process driving the paddle. I still don't know like how this thing is done, but fine. The motor exerts a torque driving the paddle at angular velocity. The pressure of the gas, constant volume, is observed to increase at a steady rate. Oh, steady rate. So this whole thing is actually constant. Fine, that's okay. Show that the energy difference between any two states of equal volumes can be determined by this process. Energy difference between any two states. In particular, calculate UC minus UA. I don't even kind of understand what's going on over here. Small paddle. What is this paddle thing? So what is C? I just don't know. Particularly upward and downward on the P-word plot. The process can only proceed in one direction. Nope, I don't understand this. States of equal volume can be determined by this process. The pressure changes fine at a constant volume, and that gives us so this is basically some sort of an isochoric process that they're talking about. And then they are saying that the energy difference between any two states of equal volumes that can be calculated uh, by this process. No, I still don't understand what's going on. Torque times omega VdP upon dt is equal to this. Energy difference. So what's the amount of energy that you have put in it, right? It's supposed to be just tau d omega, right? That's the energy that you're constantly putting in, but obviously omega is actually kind of constant, so this doesn't even make sense. Now I don't understand it. Why? And then the pressure is supposed to increase continuously. Omega is constant, your torque is constant, your V is constant. But like, why is there a torque in the first place? Okay, I just don't understand. I think I'm gonna move on because this whole thing is just weird. C is show that any two states points on PV plane can be connected by the combination of the processes in AB, adiabatic and isochoric. In particular, evaluate the energy at D minus energy at A. Okay, UD minus UA. What? Wait, so how do you get the energy at D? Well, notice that during dV there is no work, so just the heat exchanged. Okay, that is the change in energy. Sure, that does not help us in any case. Oh, come on. You know what that energy changes. You know what? The only energy change you really know is the A to B energy change, right? Oh, but you are also being given the adiabatic process, so fine. B plane can be connected by a combination of the processes. So any 2 points are connected. So this is kind of okay. So yeah, you can sort of do that. So suppose you have 2 points. There may not be an adiabat between these. So just do this sort of an adiabat and then you just drop down. So whenever you reach this volume, you just like drop down directly. Cool. So now kind of what we want is, I mean, okay, this is a bit too easy. Like all we have to show is that all volumes are available to us for this process, right? PV power, so PV power 5, V power 3 equal to constant, and they are. And if all volumes are like available, you start off at any point, you can reach every volume. Once you reach a volume, just drop down the pressure and reach this some isochoric process. Sorry, that's what you're talking about. So yeah, what's so problematic about this? What do we have to show as such? So in particular, we want to evaluate UD minus UA. UD. What is U once again? I don't kind of know. Okay, let's actually just try to kind of get some idea of what the energy might be. So you know what the energetics is for the A to P process. You also know the work done along AD. That's actually the whole work done along ADB as well. And this heat transfer, there is no work done along BD is 0. That is the only thing we really know. Come on, this is weird. Okay, let's just do it the hard way. So what you want is DE is just minus BdV, but wait a second. So you kind of know what the energy changes. Yeah. But that's only for adiabatic cases, right? You don't know what the energy change is in general, so you can't do that. Also, are we saying these can be calculated basically? Like, yeah, I guess they sure can be. Okay, so whatever point you want to go to, just like one way, just do this thing and then drop down, or you can just do this thing, that also works, or you can sort of do this thing, that also works. But how does any of this help us in the end? I don't know. This whole thing is just weird. Okay, anyway, let's go on to the next question. So C is remaining, D is what we will do. Calculate the work done, W8 in the process A to D. Calculate. So once again, we actually need to show what the work done is in A to D. How? How is the question? I don't think there is an answer. We need a hint. We need actually a hint for this, because problem with this thing is they're not given what's the equation for energy, so you cannot do anything. But we do know that this whole thing is, so maybe we can actually kind of find the expression for entropy, right? Just think of entropy as a function of pressure and volume. Then you know that cross the adiabat, and it seems to be a reversible adiabat. Yeah, right. So in the adiabatic process, a quasi-static increase in the volume results in decrease of pressure. Oh, come on, you have not told me that it's a reversible adiabat, is it? Okay, so I can't just do that apparently. The TDS equal to DQ thing, that may or may not be true though. Wait, but I already used that. To say that just assume it's reversible, because otherwise there is no way of doing it, is there? No, there isn't. How else are we going to calculate the work done, right? Okay, the work done kind of can actually calculate, no problem with that. But what about the energy change? Yeah, okay, so the moment that you say that W equal to minus PdV, you also have to say that so the moment you say this, you also have to say that dq equal to TdS. If you don't, we just get the implication anyway, right? So I guess we can kind of assume that dq is in fact TdS. And so they are saying dq equal to 0, so TdS equal to 0, ds equal to 0. But if ds equal to 0, and that implies that p power 3 v power 5 is constant, essentially what they're meaning that is 3 natural log of p plus 5 natural log of p is constant. Well, okay, ds is 0, that just means entropy is not changing, so like natural log of the entropy is also not changing, right? That's not a good idea. Okay, entropy is usually as its natural log. I don't know what I should do. How am I going to find this thing? If a TDS is 0, then there is no hope, because you only have this thing. You don't know the exact form of the entropy. You only have this one equation. How is this even relevant? Yeah, it's not. It could be any function of p power 3, p power 5, and you wouldn't know, right? For all we know, it could be something like just 2 times the normal entropy, and you wouldn't know that. Yeah, this whole thing is very vague. They should give us more equations. There is no way to solve this otherwise. I'm just gonna move on. Question number 4. They must either specify that we are dealing with an ideal gas or something, otherwise it's impossible to solve that. For a particular gaseous system, if it has been determined that the energy is given by U equal to 2.5 PV plus constant. Okay, so consider the following PV diagram for the system. Calculate Q and W for each of A, B. Oh, come on, once again PV diagrams. Calculate Q and W for the process from A. So at least now they are like giving us what U is. So they have given that U is just 2.5 or 5/2. That's better. PV plus some sort of constant U naught. U is just E basically. Consider the following PV diagram. So this is the PV diagram. I think it's A, B, C. This is at 0.5. Okay, megapascal, fine. This thing is 0.1, and this is mega is like 10 power 6, so 10 power 6 pascals. It's a scale. This thing is in meter cube. This thing is what, 0.01. This thing is 0.03. Fine, given a triangle. Cool. What about this triangle? Calculate Q and W for each of the processes. Fine. For this thing, the W thing is 0. For this thing, the W thing is just P times V. So I'm just gonna write down what W is. So process W, Q, and the energy change. Right. Okay. So the first process is like A to B, and then you have B to C, and then C to A. So AD, what's the work done? The work done is just the pressure, which is 0.1 times 0.02, so that's 10 power minus 1, 10 power minus 2, and then 10 power 6 pascals. So that's just the thing. It's 10 power 3. Okay, what about the BC thing? Right. So that's just okay. That work is work done on, right? So this would be actually negative because the volume is increasing, right? Over here it would be positive because the volume is decreasing. What is it? It's going to be half the sort of like average, in fact. Yeah, the average of this. So just the 10 power 3 thing at the same time. And so this stuff. So now the pressure is 5 times of that, right? So just 5 plus 10 power 3 and that upon 2. So just 3 times of 10 power 3. And the C to A, there is no work done. The heat exchange, right? Before, it's easier to just kind of calculate delta E. Yeah, so what's delta E for this thing? So just 5 upon 2 PV, right? Yes. So for A to B transition, it's just that basically. So just P delta V essentially. So just 5/2 of the work. I should have known. That's negative, that's positive though. Right? Yeah, it is. Cool. Pressure is just that. So it's just 5/2 of this, which is 25 times 10 power, so 2500. Right? What about the B to C transition? So once again, what is it at C? At C, it's just 5 times the base thing. So what's the base thing? The base thing is 10 power negative 1, 10 power negative 2, and then that's a 5/2, and that times of this 10 power 6. So this is just that, and that's 10 power 3, so it's 2500. So 2500 is the base energy, if that makes sense. At C, that energy is 5 times, so it's just like 4 times of this guy. So just 10 power 4. Oh, it's decreasing, so it's just negative 10 power 4. So wait, that's the C to A transition. C to transition should be negative 10 power 4. We want the B to C transition, right? So it's just 10 power 4 minus, well, at B it's 3 times of that, so it's just 0.3. Okay, I should say this thing. So okay, it's just the full transition just like 2 times, so 2 times of this energy, which is just 5000. Right, that's better. Yeah, so this energy is obviously increasing. Yeah, that makes sense. So now you have delta E and W. Just find Q. That's the subtraction. So yeah, so it's just gonna be 3500. This thing is subtract that, just 3000, just 2000. This is subtract that, work is 0, so just 10 power negative 4. Yeah, Cool. So that's the thing. Just gonna put that. So I guess I'm just going to stop for a while. I'll see you guys in the next video. Bye.